Good afternoon. So first of all, we have an exam on Friday, 1 week from today. Okay, it is closed notes, closed textbooks. You can bring a calculator and one piece of paper, 8.5 by 11, written both sides, as tiny as you can read. I don't care. You also can bring, if you find it useful, one or two set of axes made of straws, pencils, to think in 3D, work coordinate axes. Okay, so you can bring that too. All right. The topics covered in the exam are the topics covered in homeworks 1 and 2 and the first project. And if you look at the slides, it's basically lectures 1 to 5. Okay. All right. I have posted the solutions for homework 1 and 2 on Blackboard. I also posted today a sample test. Okay. And please work on it during the weekend or whenever you have time before Tuesday. On Tuesday, the plan is, instead of lecturing, I will be doing review. Okay. And so we will go over the sample test. We will go over questions on the homeworks that you may have, or any other questions. So also bring questions that you think will help you to study for the exam. Okay? Any questions about the exam or anything else? No? Also, regarding the project, somebody posted in Piazza and I answered, but just in case that you haven't seen it, regarding the report for the first project. So the idea is that you write one report, but each member of the team submits that report on its own, okay? So one report, multiple submissions, all right? Okay? All right, so the plan for today is to continue talking about least squares. We started that on Tuesday. And then we will move on to ransack, which is a way of eliminating bad data points on your data sets. And then we will move on to snakes or active contours, and depending how we do on time, I might start region segmentation. If not, that will get done after the exam, so 1 week from Tuesday. All right. Okay. So let me first again try to motivate why we're looking at least squares and total least squares. So we spent some time talking about the half transform, right? The half transform is a way of finding, and we started looking lines, and then we moved to circles and other curves. And the way we did that was by voting, okay? And we voted in a discrete set of counters that we look at as an image, but it was a discretization process. And we sort of talk a little bit about the noise problem that if we did that, right? So I want to emphasize that again and see how we are going to find the best fitting lines to the data points that voted for the half transform, okay? So here's an example of that image that will be computed when we vote. Let me darken the room for a little bit. Don't fall asleep, okay? So I think you can see faintly here the sinusoidal curves, right? So this is a perfect straight line. All the points are on the line, and they vote in this space over here. And we say that there's only one line because there's only one really bright spot, okay? And that spot corresponds to the rho and theta of this line, okay? All right, now let's see what happens if I add a little bit of noise to that line, right? So I jiggle a little bit the points of the line, okay? And now this is the image that the voting scheme creates, all right? So now we need to look at this image and figure out how many lines are in the original image, right? And again, we're looking for bright spots, but because now all of these points are roughly aligned, but not exactly aligned, they all vote for curves over here that they don't really intersect in a single point. I have this bright cloud of here of points, and I have to decide, you know, is it one line, is it 5 lines, and how many votes I have for each of these lines. Okay? All right? Now, the other side of the coin is that I might look for lines, and there are no lines in my image. Okay? Now, of course, any 2 points determine a line, right? So if I have 2 points, 2 edges on my image, those 2 edges will say, I think there is a line, right? There will be an intersection of these 2 sinusoidal curves, right? And the more points I have, the more chances are that some of them look almost like a line. Do you agree with me? Okay. So here what I have is a bunch of points that were randomly generated uniformly in the image. And this is the half transform that was produced from those points. Okay? And if we look over here, we see a lot of intersections. Right? Now, because the points are not a lot of them align, these intersections are not very bright. Right? I have only 1 or 2 not one, just 2 or 3 intersections going in those spots. Do you agree? So then I can say, well, if the number of curves that passes through a point is low, it's probably just random noise, and I don't care, right? So that all goes to find out what's the best threshold to figure out how many lines are there. Okay? Now, let's look at this in a little more principled way. Okay? And here I have a plot where in the x-axis I have a noise level, how much I am going to be moving my points. Okay. And on the vertical axis is how many votes I'm going to find in the being corresponding to the line. So I have a line, the ideal line I showed in my very first slide. And I'm going to move the points. Okay? And the amount of the movement is measured over here, is the sigma that was used to perturb those points. Okay? And over here what I'm doing is counting how many now of these curves would actually cross in a single point. Right? So when there's no noise, I have a count of 20 because there were 20 points on that line. Okay? So I have a perfect count. I had just one single bright spot. But now as I increase the noise, what you see is that, of course, the number of points that vote for that line starts to decrease. Okay? And it goes fairly quickly down. Okay? So we see that adding the noise will make a factor on how many votes I have and how to pick the threshold. Now let's look at the other example, which was I don't have really a line, but I throw points, right? And I want to generate a similar plot to this. So in that case, what would I do? What would I be measuring? What would be my axis saying? Nobody? How about number of points? These are, I throw random points. And now I look at how many of these random points happen to be sort of aligned, and they will give me a high count in the voting. So I'm counting maximum number of votes. And what you can see is that as I increase the number of random points, there are more and more chances that those points happen to be aligned in some way. And I will see a phantom line that really was not there. It's just made out of the noise. Okay? All right. Okay. So last time, we started saying, well, now I have points that had been aligned, points that had been said to belong to a line because they were all in a being in the half transform. Okay? Now I want to find the true parameters of that line. And one way to do that we saw was to write the least squares fitting error problem. Right? Where what I have here is I want to find the best line such that the sum of these errors, or the square of these errors, really, is as small as possible. Okay? And I gave you the equations for that, right? We took the derivatives, set them to 0, and then put it in matrix format, and we got this system of equations where the unknowns are A and B, which are the parameters of the line, and that will best fit this. Okay? And then I said, well, are you sure you want to use this equation? And the answer was no. Do you remember why? Is this the best way of addressing this problem?
It only takes the y values, not the xi values.
Right, so there's a bias. So this assuming that the ideal point was here, and it's moving down or up from that line, not left or right. And furthermore, this equation over here, it has a non-zero coefficient for the y. So it cannot represent lines where that coefficient is 0. Okay? So as an alternative, we say that what we want is our error model to be this, right? So now what I want to sum as my errors is not the vertical distance from the point to the line, but the actual Euclidean distance from the point to the line. Okay? So this is now perpendicular to the line, right? Okay, so let's see how we do that. So first of all, that means that I need to figure out a way of expressing the distance from a point to a line. So say I have this line over here, okay? And when we did a half transform, and we moved from the slope-intercept equation, what we said is, let's use this other equation that uses rho, which is, bless you, the distance from the origin to the line, and theta, which is the angle from the horizontal to that normal. And we say that the equation for that line had this form. And I sort of wrote it on the board on my slides, and I never asked you, do you believe this is the right equation? Have you seen it before? Can we prove that this indeed is the equation of this line? What's the geometric interpretation of this equation? Let's think of a point P on the line that has coordinates x and y. Okay? Now let's take the vector that goes from O to P. Let's call that vector P minus O. Okay? What are the coordinates of this vector? X, y, right? Okay? Now let's look at the unit norm of the line, this vector n. What are the coordinates of this vector n? A vector in this direction with length 1. What are the coordinates of that vector? What's the x, the first component of that vector? Come on, guys. Thank you. And the vertical? Sine theta. Okay, good. Okay. Now let's do the dot product of these two vectors. What is the dot product of those two vectors? X cosine theta plus y sine theta. And that has to be equal to what? It has to be equal to rho. And that's true for every point. Okay? So that's the physical interpretation of this equation. All right? Okay. Now, why did I revisit this? Well, now say I have a point Q that's not on the line, and I want to find how far that point is from the line. Okay? So I want this distance d. Okay? Let's take a line that's parallel to this line that passes through Q. Okay? What's the equation of this line using this norm form? Yes? And if I put the coordinates of Q in this equation, what happens? It has to satisfy, right? Because Q is a point on the curve, on the line, right? So, okay? So what is D? Which is what I wanted. D is xq cosine theta plus yq sine theta minus rho. Yes? Now let's write this equation slightly different. Let's write this as x cosine theta plus y sine theta minus rho equals 0. Okay? So this is the form ABC of a line, right? And what it says is I need to plug in the point Q in the equation of the line, right? But as we discussed on Tuesday, this is not just any equation of the line, right? I could multiply this by a constant, but this one has this coefficient and this coefficients being the cosine and the sine of the normal, okay? So the sum of their squares has to be equal to 1. All right? So that is why we are going to now write down our objective function as minimization of the sum of a xi plus b y sub I plus c squared. Right? Now these are the distances of all my points xi, yi to the line I'm trying to find, subject to the constraint that a squared plus b squared has to be equal to 1. Okay, so this is saying that this guy and this guy has to be a cosine and a sine. And this is saying the distance of the points. Okay? Cool? All right. So how do we minimize this problem? How do we find a solution to this problem? Before, what we did when we didn't have a constraint, we just took the derivatives and set it to 0. With respect to, what are the minimization variables? A, B, and C. Okay. Now we have a constraint, so what we're going to do is use Lagrangians. So we build a new objective that has the original one plus a multiplier times the constraint. And the constraint, I'm going to write it a squared plus b squared minus 1. Okay? So if the constraint is satisfied, this term is 0. Right? So I'm not changing my objective. Okay? I'm adding this extra variable, and that will allow me to do the constraint optimization. So what now we're going to do is I'm going to take the derivative of lambda, big lambda, with respect to my variables, which now are a, b, c, and lambda. Okay, so I have the derivative of lambda with respect to a has to be 0. Derivative of lambda with respect to b had to be 0. The derivative of lambda with respect to c has to be 0. And the derivative of with big lambda with respect to small lambda has to be 0. Okay, which doesn't fit in my board right now, so I'm going to write it. Oh, let's put it here. All right. Let's do this one. Anybody help me? Two sum times what? Plus, right? Okay, so 2's go away. Let's do the same thing for B now. And for C. Yes? And with lambda?
A squared plus b squared minus 1.
Right? So this one brings back the constraint. Okay? These ones is the ones I need to play with. Let's work first with this one here. Okay? So that says that sum of A is a constant. I can put it out. Xi plus B sum of Yi plus C sum of 1 has to be equal to 0. Okay? All right, so how much is sum of 1? N, where N is the number of points. Okay, let's call that capital N. Okay, so I'm going to divide everything by N. So now what I have is A X average plus B Y average plus C is equal to 0. And the reason I decided to play with this one is because I'm going to eliminate the variable C from the other two equations. Okay, and here C is easy to get out, right? So this one says that C is equal to minus A X average plus B Y average. So now let's plug that into the first and second equations. Okay, so the first equation says A sum of xi squared plus B sum xi was to I plus C sum of xi is equal to minus A lambda. Okay, I pass lambda to the other side. So let's plug in C over here. Okay, and also let's divide by N. Okay, so this guy actually right now means that A, the average of x squared plus B times the average of x times y plus C, the average of x, has to be equal to minus I lambda over N. Yeah? Okay. So now let's plug in C. And so what I get is that AX squared average plus BXY average minus minus X average squared minus B X average Y average is equal to minus A lambda over N. Okay? And now let me group things together. Things that have A on the right-hand side, on the left-hand side. The things that have A together and the things that have B together. So that's X squared average minus X average squared times A plus XY average minus X average times Y average times B has to be equal to minus A lambda over N. Okay? I could do exactly the same for this equation, right? I can divide by n, so the average show up, and then I can plug in C for that expression, and I will get an equation that looks very similar to that one. Let me copy that one here so it's easier. So I have x squared average minus x average square times a plus b times xy average minus x average. Average is equal to minus a lambda over n. Okay. And then the next equation would be xy average minus x average is y average times b, times a plus b times y squared minus y average square is equal to minus b lambda over n. Okay. Okay. How do I solve this? What do I know here and what I don't? First of all, make sure that we understand this notation, right? Why this term is not 0? They're different things, right? This I'm taking all the x squares, sum them up, and divide it by n. This one is I'm doing the average of x and then raising to square. Okay? So this is not 0 in general. Okay? Now, how do I solve this? Here, what do I know and what is not known? What is given? X and Y's, right? So I have n pairs of the form x1, y1, x2, y2, xn, yn. Right? These were all the guys that voted for that line in the half transform. Okay? So that means from here, I know x average, y average, x times y average, x squared average, y squared average. Okay, so I know all of this. So that means I know these coefficients, right? So what is that I don't know? Do I know A? No, I don't know A. I don't know B. And I don't know lambda. Okay? So A and B are related to the orientation of that line that I'm looking for. But I still don't know where it is. Okay? I have an idea because if I voted for the half transform, I sort of know what the orientation was, but not exactly. Okay? All right. So let me change this notation a little bit. Okay, let me define a new variable. If you didn't have enough variables yet, let's call mu. Okay, the variable minus lambda over n. Okay, let's define that. And then I will do something that I hated when my professors did, which is I'm going to erase and edit this. And now this is mu times A and mu times B. Okay. So let's put this in a matrix format. So now I have a 2 by 2 matrix that has x squared average minus x average square xy average minus x average times y average, and it's symmetric. Times a vector that has a and b has to be equal to a scalar mu times the vector a and b. Do you agree that this and this are exactly the same? Right? I haven't changed anything. Right? So why did I do it? Why did I write it this way?
Covariance matrix?
It is, yes, but that's just that matrix. But the whole equation,
Their eigenvalues?
yes, I know how to solve this problem, right? What this is saying is that A and B is a vector, which is an eigenvector of this matrix. Okay, so I know how to solve this. Okay, so the hope was that going from here to here, you would recognize, oh, yeah, I can do this, right? I have done it before. Okay, so again, the main difference between what we did on Tuesday and what we're doing here is that we changed our optimization criteria to be both in the x and the y direction. And that complicated a little bit things, right? So before it was just you solve a system of equations that had a unique solution. Over here now we ended up having an eigenvalue, eigenvector problem, but it's not much harder, right? We know how to do this. Especially this is a very small matrix, it's 2 by 2. Okay, questions? No? All right. Okay, so can I pull the screen down? All right, so again, what we just did is started from the point of view that somebody told me which points belongs to the line. And now what I needed to do is find the best line that fitted that, okay? And one way of doing that is something that we saw was the half transform, but that's not the only way, okay? So I want to mention briefly a couple of alternative ways of doing this, okay? One way is to do incremental line fitting, okay? What that means is that I'm going to have a chain of pixels that they are connected, they're next to each other, and I'm going to try to fit a line to that, okay? We're going to get that chain of pixels almost for free. Do you remember? Did we see any algorithm that would give us the chain of pixels? What did hysteresis thresholding? You guys are very quiet. So when we did the Canyons detector, right, the last step was hysteresis thresholding. And when it was doing hysteresis thresholding, what it was doing was looking for chains of pixels. Okay, so the output of the Canyon edge detector will give me these chains of pixels. Okay, now they're not necessarily on a line. They could be on a circle or in any complex curve, right? But what we can do is start at one point and see if I start adding points, the first, second, and third, are they aligned or not? And then I keep adding points and seeing whether that line is a good fit or not. Okay, so that's what incremental line fitting does. Okay, so here's the algorithm in words of what I just said. Okay, you have a chain of pixels, and you start adding one pixel at a time to a line. And when the fitting error is too large, you say, okay, I have enough. I stop and start a new line. So you can approximate a complex curve by a bunch of line segments. Okay? The other way of doing it is with k-means. Anybody knows what how k-means works? How?
I think it's trying to find.
You knew too?
Yeah. I guess if you have a bunch of data points, you start by randomly initializing 3 or however many k points that you want, and you group all the data points to the nearest set of those center points, and then you recalculate the center based on the average of all of those data points, and you do that iteratively until it converges.
Okay. Can you see that applied to lines? How would you do it with lines? Did everybody get what he said? Let's talk in 2D. What he was saying, suppose you have a cloud of points. And you knew that there were 3 clusters in that cloud of points. And you want to find which points belongs to which cluster. Okay, so in this case, K is the number of clusters is equal to 3. So what he said is you randomly select 3 points. Okay, and say I pick this guy, I pick this guy, and I pick this guy. Okay, that's a bad choice, but I did it on purpose because I don't know who belongs to what. Okay, and so then the next thing is I'm going to assign all of these points, the crosses, to the clusters that are represented by these points I picked. And I'm going to do that based on distance. Anybody that's the closest guy is this guy, I'm going to assign to the cluster of this guy. So in this case, all of these points will go to this guy. Okay, all of these, well, half of these points maybe will go to this guy, but also these guys might go to here. I don't know, I had to check the distances. And then these guys will go to that. That obviously is not the right solution, right? But then what you do is you look at the mean of all your samples. And now you pick that as your representative of that cluster. Okay? So now this guy will give me something like this. And this guy will give me something like this. And you do it again. Now you assign, given these representatives, who do belong to that. Okay? And you do it many times, and you hope to converge to the right answer, which would be, this is one cluster, this is another cluster, this is another cluster, and the representatives are the centers of the class, of the clusters. Okay? Now, it's a really nice algorithm. It can converge quite fast. However, there are no guarantees that you converge to the right solution. Okay? And in fact, what people do when you use this is you do it multiple times. Okay? And so if you do it not many times, you hope that at least several times will be the right one. And when you see that you're always converging to that same solution several times, you say, well, probably that's the best solution. Okay? All right, so that was for points. How do I do this with lines? So I have 3 lines again. Okay, so somebody told me how many lines I have, which is, again, a nice thing that the half transform doesn't need to be tall. the half transform can figure out on its own most of the time how many lines you have. Here, I tell the algorithm I have 3 lines. Now, please tell me which points belongs to which line. Okay. So again, what we can do is initialize. Okay. And you can do it different ways. You can randomly throw 3 lines in the space. Or you can pick pairs of points and do a line with a pairs of points. Okay. And do I don't know. And now what I do is assign points to the line based on the distance. And now we know how to compute the distance from a point to a line. It's very easy, right? We have the equation of the line. We just plug in the numbers in there. We get the distance. And then if the distance, so we assign the point to the line that is the closest one. So like this guy is closest to this line, so it will be associated with that. Okay? And now that we have associations that we know, we think we know which point belongs to which line, we apply what we just did. We find the best line for that set of points. And then we reiterate and we reiterate. Okay? So that's another way of doing k-means, but now for lines. Okay, so that's exactly what I just said. All right, now, all of this presumes that the algorithms are going to find the right assignment between points and lines. Okay, what we're going to talk next is what happens when we have outliers. Okay, and what outliers are points that do not follow the general trend. Okay, so I have all of these points that you would think they fit to a line. But if I told you that all of these points belong to a line, clearly these 2 guys are not fitting. Okay, they're not following that model. Okay, so we're going to call these outliers, and these guys we're going to call them inliers. And the problem that we're faced with is that if we try to fit a line using either least squares or total least squares with outliers, we're going to get really bad results. Okay. So here is an example where they have those points I just showed you, right? It has the inliers plus the outliers, okay? And if you throw that into the algorithm and says, find me the best line that fits all these data points, okay? The algorithm struggles to try to make everybody happy, but nobody's really happy, right? So I have a lot of large errors. Okay, and so the orientation of the line, instead of being this one, which would be what we have here, it has been twisted. It has been moved by these 2 gross outliers. Okay, so clearly outliers are a problem. Okay, and people have been doing research since forever on how to try to clean those outliers. Okay, so here's another example. So I have these points on this line. Okay. You throw an outlier, and now the line is very bad fitting, okay? Or this other case. And this doesn't look so bad until you zoom in. When you zoom in, you really see that the line is really off, okay? So outliers are a pain, okay? So we want to remove them, okay? Now, outliers by themselves is not just the only problem when we're faced, okay? Another problem is it might be that I have the wrong hypothesis about the number of features I'm looking for. Okay? So if I have these very pretty perfect data points, the blue and the greens, that are 2 parallel lines, but I tell my system, go and find 1 line, do a total least squares on this, I will find something that looks like this, okay? Which clearly is wrong. Okay, so not only the points are off because they're not on the line I was saying, it could be because I have the wrong number of lines. Okay, so we're going to talk about a couple ways of addressing the issue of outliers, not of the wrong model, but of outliers. And I listed also another one that we're not going to cover in this class. So there's something called expectation maximization that can be used to remove outliers. We're not going to talk about that today. But I'm going to talk about two other approaches that are fairly easy to implement. One is the M-estimator, and the other one is RANSAC. Okay? And the idea behind these algorithms is very simple, very intuitive. In the case of the M-estimator, okay, what we're going to do is we're going to modify our objective function that we're trying to optimize. Okay? So if you remember, Ayer is behind the screen, or I erase it, but the way we started with the total least squares was we sum the square of the errors and we minimize that. Okay? So that means that a large error is bad. Okay? And if you look at the examples I gave you with outliers, like here, right? What happens is that these errors over here are going to be very large. Okay? And by trying to minimize these guys, right, the algorithm settle in this sort of, not good for anybody kind of line. Okay? Now, if I didn't have these errors, or if you realize these errors are already pretty large and I ignore it, then I could have moved the line closer to the inlier points. Okay? So the idea is that I'm going to pay penalty for these errors, but as long as they're reasonable errors, something that I can expect that happens because of noise. But if the error is very large, it's probably an outlier, and I refuse to pay too much for it. Okay? I'll pay something because I don't know if it's an outlier or not. Okay? But I will threshold how much I pay. I will put a bound. Okay? I will say enough is enough. I don't have more money to pay you for this error. Okay? So here is the modification that we're doing to your total least squares or to the least squares. Doesn't matter. What it's saying is we're going to minimize the sum of some errors. Okay? The errors are these R's. These are the residuals. It's the difference between what it should have been and what it is. Okay? For each data point, I measure how far off I am from the line I'm proposing or the circle I'm proposing. This is actually very general. It could be for any optimization. Okay? So Ri is the residual. Xi's are the samples, and theta are the parameters of the model I'm trying to fit. So if I'm using total least squares, is the A, B, and C's. Okay? If I'm using least squares, is the M and N. Okay? So theta are the parameters. R is the residuals. So before, what we had over here was the square of the residuals. Okay? So now instead of minimizing the sum of the squares of the residuals, what we're going to do is minimize a function of the residuals. And that function can be tuned with this parameter sigma. All right? And here is an example of a row function that can be used for doing that. Okay? So it looks like this. So look at this curve over here. All right? This is the parabola for y equal x squared. That is the objective function I was using when I was doing least squares or total least squares. Okay? Now, what we're proposing is to, instead of using that cost function that goes very high very quickly, right? What we're going to do is saturate the error. So as the error becomes larger, we're going to flat out. And how quickly we flat out is controlled by sigma. Okay? So the idea is that the curves around here in the small errors, they are close to yx equals square. Okay? It's close to my least squares. But if the error becomes too large, I'm going to saturate it. Okay? That's the only difference. Now it's a big difference. Yes? No, I'm not ignoring. I'm making it, say, 1. Okay? I flatten out. So yes, so I know I have a bad point, and I'm going to pay for it, but I'm not going to pay 1,000. I'm going to pay something, right? So the more bad points I have, the more I'm paying Okay, so they do have an effect. But I'm just trying not to have those points drown the good points, right? So what happens is that error for those bad points, if it's too large, it will drown the other ones, and so it will make everybody to be large. Yes?
Why not just set a threshold and ignore it?
You could do that too, okay? Now, the thing is that with this, then you can differentiate, right? This is a continuous curve that I can differentiate, and I can do my Lagrangian like before, okay? So, however, there is a problem with that. And the problem is that this function now is not a linear function anymore. So before, I got a really nice eigenvalue, eigenvector problem. Once I put this in, that goes out of the window. I cannot do it in closed form solution anymore. I have to do an iterative procedure. Okay. So this is what just I said. The other problem, of course, is that you need to figure out what sigma is, right? And picking the right sigma can be hard. So let me show you a couple examples. So this one over here, if the sigma is too small, I still get the bad line. If sigma is large, I also get the bad line. If sigma is just perfect, I get the line I want, right? So finding the right sigma can be also tricky. Okay. And that's why we're going to talk about the next method that is a little easier to implement. Okay? Questions? No? Okay, so let's talk about RANSAC. Okay? RANSAC stands for Random Sample Consensus. Okay? And it's an approach that, again, that is tailored to find bad apples in my data. Okay, so I get a basket of data, and I want to figure out which ones are the rotten ones. Okay. So again, it can be generalized for other things, but let's talk about this in terms of lines. So these are the data points I got. Okay, and I want to fit a line to these points. Okay. So RANSAC, what it does is going to pick randomly 2 points of my data. Okay? And it's going to throw a line through those 2 points. Okay? 2 points is the minimum number of points I need to give a line. And now I'm going to count how many points of my data are close to this line. Okay? So I have a band, and I have to decide that threshold. Okay? So I changed the picking the sigma for picking this threshold, right? But there's no really free lunch. I need to do some decisions here. But I pick this band, and then I count how many points are within that band. Okay? So in this case, I count 4 points. Okay? These the 2 guys that I started with, and these 2 red points. Okay? So I have an evidence of 4 points that say, I think this line is the line I'm looking for. Okay? Now, let's try it again. I pick 2 other points. And now I look at how many are in that band. And now this time I have 6. So, maybe this line is better than what I had before. And I do it again. And this is really good. I have 19 points. Okay? This has 13 points. So, of all the times I try, that guy that had 19 seems to be the best bet. Okay? So it looks like a very brute force kind of approach, right? How many times do I have to try to get a good line? I'm sorry? N squared? How? So I have n points, and I have to pick 2. So it's n choose 2, okay? Which is roughly n squared over 2. Okay? So it would be a lot of trials, right, to do an exhaustive search. Okay? Now, the beauty of RANSAC is that I can get away with much less trials, with many fewer trials than just trying every possible thing. Okay? That's the beauty of RANSAC. Okay? Let's see how we do that. Okay. So this is the algorithm. Choose a small subset uniformly distributed from the data at random. Then feed to that whatever I'm looking for. I did lines here, but it could be circles. Okay. Anything that's close to what I'm trying to fit, it's presumed to be an inlier. Everything else I presume to be outliers. And we do refitting and do this many times, and we choose the best. Okay. Now, how many times? That's a question. Okay. The answer is often enough that we're likely to have a good line. So obviously, if I did it exhaustively, I will be guaranteed that I find the best line. Okay. But I don't want to do exhaustively. I want to do often enough that with some probability, I will get a good line. How big is the subset? The smallest possible. So for lines, it's 2 points. For a circle, it will be 3 points. How does close mean? Well, it depends on the problem. For the line, it's clear. It's the distance from the points to the line. Okay? And what is a good line? Is one that has enough good points. Okay? So here's the algorithm. But before that, let's look at how many samples to choose. And I said the worst case would be doing n choose 2. Okay? Now we can do with less of that. So for that, let me show you an equation. And that equation will depend on these things. Okay? First of all, let's assume that I have some idea of the probability that a point is an outlier. Okay? So I know, maybe 20% of my data points are really bad. I don't know which ones, but I have an idea of how many I can expect. Okay, so that's E. I also know the number of points in the minimum sample. In my case, for the line was 2. I'm going to call that S. I also know how many samples I'm given. I'm calling that capital N. And then I have a parameter that I need to choose that says, what is the probability that I want to be assured that I will get a good line? Okay, so maybe I say P needs to be 99%. Okay, so 99% probability that I will get a good line. Okay, so based on that, we're going to derive this equation. Okay, this equation says that if you're given n samples, and the minimum number of samples that you need for fitting the model is little s, and if the probability of outliers is E, and you want a guarantee of having found at least one good line or whatever we're fitting with probability P, okay, this needs to be satisfied. Okay? So if you give me P, right, I can find out the rest over here. Okay, so let's see how it does. Okay, so 1 minus E is the probability of choosing one inlier. Remember, I have n points. Okay, and out of those n points, let's pick one. The probability that that's an outlier is E. The probability that's an inlier is 1 minus E. Okay? So this is the probability of choosing one inlier. Okay? Now, how many inliers do I need to pick a good line? S, right? 2 in my case. Okay? So assuming that I pick these guys independent of each other, the probability of picking 2 inliers is going to be 1 minus E squared. Okay? Or in general, 1 minus E power S. Okay? So that's the probability of picking the minimum number of points I need, and all of these are good points. Okay? All right. Now, what is the probability that at least one of those points is bad? One minus that. Okay? So this is the probability that at least one or more of points on the samples have an outlier in it. Okay? And now I'm going to do n times. How many times I'm going to be doing this? Okay? That's the number of times I want to try. And I don't want it to be n choose 2. Sorry, I'm using n for 2 different things. Here, n is the number of trials let's call m the number of samples, okay? So this n over here is how many times I'm going to try that, and I want that to be less than the number of samples choose s, right? So I'm going to try this n times, so that's power n. And now the probability that at least one of the trials is good is 1 minus that. Okay? So all of that to say that if I try this big N times, okay, I will have a good sample, okay, with probability P. So I can set P and figure out how big N has to be. Okay? So we know that for P equal 1, N is equal to the number of samples choose S. Right? Because that, for sure, we will have a good sample there. Okay? Now, what's surprising about RANSAC is that N doesn't have to be very large. Okay? So here's a table that has in the first column the minimum number of samples that you need in a sample. Okay? So when we're dealing with lines, we're dealing with the first row of this table, S equal 2. Okay? But as I said, circles need 3 points, and other things need more points. Okay? And then following columns is the probability of outliers. So as I move from the left to the right, I'm increasing the number of bad points. Okay? So this first column has 5% of outliers, and the last column over here has 50% of outliers. That is, half of my points are bad. Okay? And look at the numbers on this table. Okay? If I have only 5% of bad samples, it's good enough, okay, to have a 2 samples, okay, to have a probability of 0.99. Okay, so I try 2 times only, and I have 99% probability that one of the 2 lines is a good line. Okay? So let's look at the example I had before. I had 12 points, so the number of samples is 12. The sample size is 2 because I'm looking for lines. Okay? And let's say I have, well, in this case I have a couple of outliers. So the probability of E is 1 over 6, which is around 20%. It's not exactly, but around there. And looking at the table back, right, with 20%, n equals 5 will give me 99% chance of having a good line. Okay? And so that's 5 trials as opposed to 66 trials, which had been the brute force, trying every possible combination of 2 points. So that's a significant saving in time. Can I be certain I will find the right line? Of course not. This is in probability, right? 99% doesn't mean 100%. So I might be unlucky and try 5 times, and none of the 5 ones is the good one. Okay? So I probably want to do a little more than that, just to be certain, especially since these numbers do not increase so quickly. Okay? So again, the algorithm is, I figure out how many times I need to do it. I pick these random samples, and I count. Okay? And then I pick the one that has the most votes, the one that it has more consensus. That's why it's called random sample consensus, right? So we're looking at, for confidence from all the data points, that the model that I pick randomly is the right one. Okay? Now, how we can do this also is we can stop by figuring out how many good points are assigned to a line. So if I know what is the probability of outliers, that means that I know roughly how many of the points are inliers. Right? So a good line should have assigned to it roughly the number of inliers. So if I see that, I can also stop. Make sense? Am I done when I finish that? Well, I can do better. So once I figured out that the line I pick, say with these 2 points, A and B, and it had a lot of confidence of the other points as being inliers, meaning that this guy and this guy are outliers, what I can do is now fit a better line to all my inliers. Okay, so I go back to my total least squares or my least squares. So I clean up the bad data. Now I know I have data that's only perturbed by some small noise, and I feed my best line to those data points. Okay? Yes? All right. As I said, this can be generalized to other things. Now, that's easier to be said than done because we need to, first of all, have a parametric format of our curve that we're trying to fit. We have to have a way of measuring the distance from the points to our curve. Okay? So lines are easy. Circles are okay, but as we get to more and more complicated things, it's harder to implement. Okay? All right. Any more questions? No? We're switching gears now. We're moving into finding now boundaries, contours. So, and one method I wanted to discuss today is something called snakes or active contours. Okay? And here is an example of a snake being used to follow the contour of this leaf as the leaf moves in the wind. Okay? So what we want is to have a contour, a boundary of an object. That object is moving. It could be actually also distorting because of flexibility of the wind. And I want to be able to have that contour at every frame. Okay? So as I said, they're called snakes, active contours, the formable contour. All of these names means the same thing. Okay? And one way of thinking of these contours is as thinking of an elastic band. Okay? So I have, my contour is flexible and it's springy. Okay? It's like a rubber band. And what we're going to do is we're going to stretch it so it hugs the object that I'm trying to segment out. Okay? And to hug the object, well, it has to be sensitive to the grading in the image because the boundary of the object is when the grade levels are changing. So my algorithm is going to move this snake. Okay? It's going to crawl in the image like a snake. That's why they're called snakes. And it's going to try to get to the warm place of places where the gradient of my image is high, because that's where the contour happens. Okay. Now, at times I will talk about in continuous domain, but really when we're doing this in an image, it's a discrete snake. So instead of a snake or a elastic band, you can think of a necklace of beads, okay, that they are all gathered together by a elastic in between. So the necklace is made of a elastic band, and I have beads on that elastic band. Okay, so that's the imaginary. Okay. So the good thing about this is that I don't have to know a priori whether I'm looking for a circle, a triangle, or any crazy shape. Okay, so it will find the boundary, no matter what, of a closed forms region, and it does so by solving in between quotes an optimization problem. Okay, what it means is that I'm going to have an objective function that measures how good the snake is doing the job, and I want it such that that cost becomes as small as possible. Okay. Now the trick is that the optimization cost that I'm going to write down cannot be solved using Lagrange multipliers, and I cannot have a closed form solution. I will not be able to do an eigenvalue, eigenvector problem like I did for the total least square. It will be an iterative procedure, okay? And it will be, it can be trapped in local minima because it's not a convex problem, okay? But the idea is to optimize something, okay? So what we're going to do is, instead of finding the edges and linking the edges, we're going to drop the snake on the image, and we're going to let that snake move. So let me show you first an example. Okay, so let's say I have this image of this chess piece, okay, which I want to segment. In this case, is very easy to segment in the sense that I have very nice contrast between the object that has been all set to white and the background to black. Okay, so finding those edges and linking those edges might not be as hard in this case. But the idea here is that I'm going to be dropping a snake, and I can do this manually by clicking with the mouse around it. Okay, so these red dots are the beads of my necklace. Okay, and the only thing is I have to do is make sure that it has a whole object inside. And now what I'm going to do is these red dots to move. Okay, so at each iteration of the algorithm, the dots are going to move. And what I want is that at the end of the algorithm, they're actually hugging the chess piece. Okay? So to do that, I need this optimization cost I mentioned. Okay, what I'm going to do is I have to measure how well that snake or how bad the snake is doing the job I want. Okay? And I'm going to try to minimize that cost. And I'm going to consider a couple things to do this. Okay? I want the snake to hug my object. I also want the snake to remain complete. I don't want it to break. Okay? So what we're going to do is have this energy function. Okay? And the way I'm going to define is that I want to go to smaller values of E. Okay, so the best place for my snake to be is when the cost is basically 0. Okay, so I start with some cost when the snake is randomly put, and as the snake moves, the cost goes down, 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 down. Okay? All right. So here we're going to design this function. Okay? To do that, we're going to consider a set of forces that are being applied to the points on the snake. Remember, the snake was like a necklace of beads. Every bead will have forces acting on it. Some of these forces are pulling the snake towards the contour, and other forces will be pulling to stretch the elastic band. Okay? So we have these forces that are internal to the snake and forces that are external. The external come from the actual content of my image. All right? So I have internal forces and external forces. In the equilibrium, these forces will balance. Okay? And so I will stop. When the forces are not balanced, it will be pulling the beads, and the beads will move. Okay? So it's a very physical analogy for the computational algorithm. Do you understand what I'm saying? Okay? All right, so let's look first to the external force. Okay, I want my snake to be attracted to contours. Contours happen in boundaries. Boundaries happen when the gradient of the image is large. So what I want is that my edge pixels, the places where my edge detector says I have a high gradient, a magnitude of the gradient, I want my snake to go there like, I want to be warm. I want to be there. Okay? So what we're going to do is we want a force that is proportional to the magnitude of the gradient. The bigger the gradient, the bigger the pull. Okay? The stronger the edge, the stronger the pull or attraction of the snake to that point. Okay. Now, for the internal forces, I want, first of all, the snake is a close contour, so I don't want it to break. I don't want one bead to be pulled so far away that the elastic band that is holding my snake breaks apart. Okay. So I have to have something that if somebody goes too far, its neighbor saying, don't go, stay with me. Okay, so we will have a force that has to be proportional to the distance between consecutive points. Okay, the farther apart they are, the stronger the pull is to be coming. So you can think again like having springs between the beads. Okay, so these two forces are fairly clear. Okay, I have a force that pulls me to the edge. I have another force that says, well, yeah, don't go all crazy, 1 point here, 1 point there. It's a contour, okay? The third force that we're going to think about is that the contours that we're looking for in real life tend to be smooth. So I don't want my snake to be very jumpy, with a lot of curvature, okay? So we are going to have another force that's trying to smooth out, okay? So if something is making like a corner, it's going to try to make it more like a circle, okay? So that force preventing oscillations is going to penalize high curvature, and curvature is given by the second order derivative, okay? So this is the diagram that I have been talking towards, okay? So these gray dots over here are points on your snake, okay? And this point over here is a point in your image that has a very high gradient magnitude, all right? And so each point on the necklace has forces acting into it. It has some attraction to the contrast edge, but also it has forces that are keeping it near its neighbors, and also forces that try to make this as flat as possible, because I don't want this corner, okay? And so as long as these forces do not balance, there's going to be movement, okay? Think of physics, okay? You have a point that has forces into it. If the sum of the forces is not 0, the point moves, okay? And the idea is that every point on the snake is subject to these forces, so the snake is moving and deforming as they move. And at some point, it will reach balance. And when it reaches balance, hopefully is where I want it to be, hugging my contour. Okay? That's the intuition. All right. So I can put this in a little fancier equations, but what it says is, if I have here my snake, at every point on the snake, I have a set of internal forces and external forces. I sum them up, I integrate it over all the curve, okay? And this is my overall energy. And when the thing finishes, this energy is very low, it's 0, because all the forces match each other, okay? Now, we don't work with integrals, we work with sums. And so here what I have is an energy function that has 3 terms. The first term is the continuity, the one that keeps the snake from breaking apart. I have a middle term here that is the one that is stopping for having high curvature things. And this one over here is the one that has the edginess. Okay, and then here's where I depart from physics. Now this is a computer algorithm that I'm designing to segment my image. So now what I'm going to choose is to give more importance to some of these terms and less importance to others. Okay, so these A, B, and C are knobs that I have to alter the behavior of the algorithm. Okay, I'm paying more importance to edginess than the smoothness. I raise this C constant over here. If it's, for me, it's very important that it has to be smooth, then I raise B. Okay? So these are knobs that I have. All right. So let's look a little more at the precise equations for these terms. Okay? So let's revisit them again. Okay? So for the snake not to break apart, what I would like is actually that all my bits are equally spaced. Okay, so if I look at the distance between consecutive bits, I would like that distance is more or less constant around the snake. So any deviation from that, I'm going to penalize it. Okay, so my force here is given by D is the average distance between points. And this is the distance between 2 actual points, Pi and Pi minus 1. Okay, so I'm looking at a point on the snake and the previous point, looking at the distance, the vector between those two, compare against D, okay? And if they are the same as D, there is no force. The thing is nice, it's evenly distributed. But if there is a big difference, then the snake is trying to correct that. It's going to try to even out the distribution of the points, okay? So the term for the continuity in the energy function becomes just this expression. D is the average distance between points. This is the distance between consecutive points, okay? And then square them up because, again, I want this to be always positive. Okay? Now, for the smoothness one, I said I want to prevent big corners. And that is, I want to have a small second derivative. Okay? And this is the discrete approximation using differences of doing first order derivative and then first order derivative. So you get the second order derivative. Okay? And I want, again, this term to be small. So this is the smoothest one. So I have the first two terms, continuity and smoothness, that are both internal forces. Now I need to look at the external force. So what would be the external force term? It has to be proportional to the gradient, right, to the magnitude of the gradient. And anything else? This term is positive, right? And so at the best it can be, if I'm trying to minimize, it's going to be 0. The previous term also, the best it can be, it would be 0. Now, I do want to be at a place which has h, right? H has large gradient. So just having the large gradient, what we will make is my cost go up. I'm trying to minimize my cost, right? So what can I do to fix that? I put a minus sign in front. Okay? So large positive, I make it into a very small negative number. Okay? So now my cost function is the sum of two positive things and a negative guy. And I'm trying to make those things balance. And again, it's going back to the equation where I was saying the forces are competing and then trying to get to equilibrium. Okay? So this is an example that tries to show in a cartoon way how the coefficients A, B, and C in my cost function will affect the performance of the algorithm. So if I put a lot of importance on not having corners, then I will get something like this, right? So if my snake starts with this, instead of hugging the two circles, it's going to remain far from these edges because it's paying more attention not to having the kink, the corner of the two circles. If I start allowing for cornerness, okay, and I give more importance to edginess, then I started getting something like this, and I can go all the way to this. Okay? So I have a cost function. I had three terms, two internal forces, one external force. I want to move the snake in a way that that cost function is as small as possible. Okay? Now, what we're going to do is we're going to solve this optimization problem in a greedy way. Okay? What we're going to do is we're going to drop the snake and move the points one at a time. So this is my image. Say I have that's not going to look okay. Say I want to segment this. Okay. So I really would like to have a boundary that is that. Okay? So what we're going to do is we're going to drop a snake around it. And then we're going to let these points to move in the image to get to where I want it to be. Okay? So how we're going to do this? Well, we're going to pick one point at a time and decide where I should move this point. Okay? Where do I move? How do I know how to move? Remember, it's not just the gradient, right? So I have defined this E function that has a term for smoothness, for continuity, a term for smoothness, and a term for gradient. Okay? And I want this to be small. Okay? Now, I can compute this function at any time. Okay, so this function is a function of the location of the points on the snake. So for this snake configuration, I can compute what E is. Okay? Now, what I want to do is move this point in a way that E goes down. Okay? Now, I'm saying I'm doing this greedy because I'm going to be doing this one point at a time. And if I move this guy to what would be, looks like the best location, I might be messing up where this guy should be moving, right? So I'm not doing it in a global way. I'm doing one at a time, okay? So that's a flaw or a weakness of this approach. Okay, so what I would do is take this guy and then look at the neighborhood around this guy, okay? Now, this guy happens to be in the boundary, but suppose my image was even larger, right? So let's say I look at this 3x3 neighborhood around this guy. And I say, if I move you to here, how much is E? If I move you here, how much is E? Or here, or here, or here, or here. And I pick the movement that makes E go down. And I say, okay, let's say it was this guy. Let's move you here. And then I move to the next guy on the snake and do the same thing. And I move it. Okay? And I do that for every point on the snake. Okay? And that would be my new snake. Okay? That's one iteration of my algorithm. How do I know when to stop? When there's no more change, right? So I try again and I don't see significant change. Maybe I change 1 point, but so I can say, if I don't change more than 10 points, stop. Okay? So that's my stopping condition. Okay? Now, this shape I draw over here, it does have corners in it. Right? It has a sharp corner here, here. It's full of corners. Okay? So I actually want corners in this case. Now, what I can do is have something in between of not having corners at all or having a few corners. So what I don't want is something that goes crazy like that. But a few corners now and then is okay. So one thing I can do is, after I have my snake, I go and check each point to see if it's a candidate for a corner. And if the curvature is very large there, I have a strong suggestion that that may be a corner. What I'm going to do for the next iteration, I'm not going to penalize too much that corner. So what I'm going to do is I'm going to turn down the knob for the smoothness for that particular point. Everybody else, they need to behave. But this guy, I let it be. Okay? And I keep doing that. And that's basically the algorithm. Okay? Questions? Yes?
So just minimize the energy of that pixel, do you tear out the adjacent one? Because you change that position, you will change the.
So that's, as I said, this is a weakness of this approach. What I do is I check one edge at a time, one snake point at a time. Okay, so I move this guy, and once I move this guy, now I'm trying to move this guy. All right, and then I'm going to move the guy to the same place I moved this guy. So that means that this guy cannot move here anymore. Okay, and that might be bad. Actually, it would have been better if I let this guy move here. Maybe it didn't improve E as good, right, as much. But then it would have let me this guy move here, and that would have been better. But I didn't know because I have not looked at this point yet. So that's the weakness of this approach. I'm doing one at a time. Okay, so I'm committing to changes that I might regret later. But so be it. Okay, hopefully maybe the next iteration will fix it. Again, no guarantees. Okay.
Is it guaranteed to stop?
Well, you can stop it because you can put a maximum number of iterations. So it's, you give up after so many iterations, and and the other thing is, again, if not enough points move, then you say you stop. Okay. Again, for the snake to move, needs to have some kind of gradient that's pulling it, right? So if I don't have a gradient there, right, and I just drop a circle with my bits, smoothly distributed on my snake, and the image is constant, there's no gradient in it, the snake is very happy, right? Because everybody's equally distant from each other, right? And there is no push to make it. Okay. Right? It's a good place to stop, given that on Tuesday we will have the review session. There's no point of starting region segmentation. So again, for Tuesday, please look back your homework. Look at the mistakes you made when you solved your homework, and see if you have still questions after the grading of the TAs. And do work out the sample test. Okay? The format of the sample test is the same format of the exam. So there will be 4 questions. The first question is true and false, and the others are problems. Okay? I don't know how to say it. So most of the time in the exams, people where loses most of the points is in the first question, the true false. Okay, so pay attention to that. Don't think, oh, it's true false. I can do it. That question it gives always a hit in the grade of people. So pay attention to it. Okay. Have a good weekend.